All right, good afternoon, everybody. I'm Gene Bohensky, the Director of Application and Partner Learning for Perma. And this afternoon, we're going to be going over the second part of our series on Perma tubing dryers. We're going to talk about the best practices of how to integrate them into your system or your experiment. So I'll just go right into the introduction. As I mentioned before, for over 40 years, Perma and Nafion gas sample dryers have been successfully designed into a wide range of SEMS and analysis equipment, and they're used in many scientific experiments. The main application is the replacement of desiccant or the Peltier or compressor gas cooler to solve water problems. And Perma is the world's only manufacturer of Nafion tubing. It makes us unique in the world. In this presentation, we will cover the best practices when integrating Perma dryers into analysis equipment and experiments. So let's just review shortly how Nafion dryers work. Nafion dryers, they work like a heat exchanger. It's a simple tube in shell design that functions with water vapor similar to how a heat exchanger transfers heat. The sample gas flows through the inside of the tube, and the dry purge gas flows outside of the tube in the opposite direction in the shell. So you could see there in the diagram that the sample gas goes through the inside of the tube. That's the dark blue tubing. And the purge gas is the light aqua blue that comes in from the right and exits to the left in counter current with the sample gas that enters to the left and exits to the right. The two flows are sealed off from each other, so there's no mixing, so you're only taking the moisture away from the tubing. The Nafion dryers are available in a wide range of dryer lengths and tubing diameters, and these are chosen on the basis of how much water that needs to be removed from the sample stream and how great the flow is. And there are materials available in polypropylene, fluorocarbon, and stainless steel based upon, or you choose them based upon either the corrosion resistance required from the corrosives in the sample gas or the operating temperature of the dryer. So let's go into best practice number one. The best practice number one is really to understand your target performance level. How dry is dry? I covered this on the last presentation, but I want to go through it again because it is important that we really understand how dry we want to get the sample gas to be. So we look at these drying levels in four large levels. The first one is basically to prevent condensation or damage to the sensor. That's to knock out any moisture in the sample gas that would condense on the sensor. Most of the time we're taking, or many times we're taking samples from areas that are hotter than the ambient temperature. And many times analyzers are placed in an air-conditioned cabinet or trailer. And as a result, or it could be even in the medical field where you're taking a sample from somebody's breath, that's obviously body temperature, 37 degrees C, 98.6 Fahrenheit. And you have much more water in the sample gas that could condense out in a cool cool ambient environment. So that's why we want to knock out that moisture level. The second level is to remove moisture from most SEMS and particle monitoring applications, or any application where it's good enough to use a standard Peltier or compressor style cooler. Compressor coolers work by cooling or chilling the sample gas and removing the water as a liquid condensate. And so that's a relatively easy dryness level for Perma dryers to reach, but in many applications it's totally acceptable, and that is a common level that we need to get to. The third level is to eliminate water interference for near-infrared and improve SEMS performance. There we go to a target dew point of -10 or -15 degrees C. That's also a relatively easy target to reach for a Nafion tubing dryer. and is one of our most common performance levels. In fact, a lot of our analyzer companies that use our product to dry ambient air to use in another process, for example, they typically run the dryers to get a dew point of like -15. And the fourth level is ultimate drying for IMS, that's ion mobility spectroscopy, and other methods. There's other methods where you need to eliminate the water almost entirely. There we see a target dew point of -40 or -60. We even have an application for a hydrogen generator that's -70. This is challenging for a Nafion approach, or you can also use a dual method drying system where the Nafion dryer knocks out 98% of the water and extends the life of the desiccant, making it usable. So the next best practice is to determine the true characteristics of your sample stream. Now this sounds very simple, but in our experience, a lot of people don't really understand how much water is in the sample stream. And we also have to know, number one, the chemical composition of the sample gas and what components you are measuring, if any. It's important to know the components because that also affects on the level of dryness level required. And of course, it helps us pick the right dryer for corrosion resistance. We also need all the characteristics of the sample gas in terms of its flow rate, pressure, its temperature, and the water content in dew point or parts per million. And is it a continuous or batch application? So I mentioned before, all of our performance data is based upon continuous applications. That is, you have a continuous stream of gas with a known level of moisture in it, and that's continuously moving through the dryer over 30 minutes or an hour. And then you have a continuous stream of purge gas that is going in the opposite direction, also with a known temperature and dryness level. That's how we get our performance data. We let that go into equilibrium. We're measuring the actual amount of water in the exit sample gas, and there we come up with our performance data. Number 4, note, often the true characteristics are different than the specifications. So if you're dealing with a SEM system or dealing with some kind of process system and you're getting a spec of what the sample gas moisture level is, or you have an idea from somebody else what the sample gas moisture level is, it is our experience that oftentimes these numbers are not correct. And in real life, the amount of water that is in the gas stream is much more than what was known or what was disclosed. Of course, when you're dealing with sample gas coolers, you have to be careful because if you specify a sample gas cooler with a specific water removal rate and you exceed that, you can easily overwhelm the cooler and get to a lot of problems where you have liquid water spitting out through the at the end, and you don't really want to deal with that. With PermaPure dryers, they are actually very forgiving. They can adjust to those parameters pretty well, and which is another positive for them. But we usually like to err on the side of being conservative with selecting a dryer because typically there's more water in it than people say. So determining the true characteristics of your sample stream is extremely important. Here is a little graph of water vapor saturation temperatures and just how quickly, as you increase the temperature, how much water you get in there. We like to look at these levels too in terms of drying, and from the SEMS perspective, for example, a wet scrubber system will have a saturated dew point of 70 degrees C. That's roughly 30% water. A natural gas combustion is at 10% water or 46 degree dew point. A thermoelectric cooler, there you go, is 0.8% water or at 4 degrees C dew point. And a Nafion dryer system gets you to a -18 degree dew point for 0.12% water, which is roughly a sixth or a seventh of the water of the cooler. So the third best practice is to understand our performance data and using the dryer wheel for selection. So we have all of our performance data that we created has been graphed on this very easy drying wheel. These are also in the catalog sheets and on the website. But the drying wheel is interesting. Most of you guys have one. It's a simple tool that uses the flow rate and the target moisture level or dew point that contains Permapure's published performance data. Now, it's also why it's important to understand the data is to understand where it comes from. It's based on 20 degrees saturated air at a 20-degree dew point, and it uses minus 40-degree instrument air as the purge gas in 2 times the flow of the sample gas. The performance ratings are very conservative, and it's important to use these as a baseline. So that's the performance that we're going to start with. And anything we do to modify the dryer from there is most likely going to increase the size or increase the amount of Nafion to improve the performance from there. A couple of things I want to talk about the dryer performance. A lot of our customers in general oversize the dryers because they find that oversizing the dryer improves the performance of the dryer in their application. And that's one of the things I learned when visiting so many of our customers. They kept sizing the dryers and doing things against our advice, and then we realized we weren't providing the best advice. We had to learn from them how to change the way we looked at sizing dryers. So let's just look again at the Permapure performance curves. I mentioned this in the last presentation. When you're looking at our performance curves, on the x-axis you have the flow rate, and on the y-axis you have the target dew point. I mentioned before, if you want to go find the dryer you want to look at, let's just look at that central curve in the middle. We'll make a different dew point this time. Let's say we only want to get to 0 dew point, and you have a flow rate of 1 liter per minute. You could see that the 24-inch, it doesn't quite get there. It gets you to about a dew point of 1, but but the 48-inch there will get you to a dew point of -5. So here's the 24-inch, and then here is the 48-inch version of the performance. You know, the performance is strictly related to the amount of Nafion surface area. If you double the Nafion surface area, you can double the flow rate and get the same performance. So the next best practice is to understand what affects the performance of the Nafion dryer. So here our friend John Dalton, that means a lot for us. He came up with the law of partial pressures, that the sum of the pressure of a gas mixture is equal to the sum of its partial pressures of its individual gas components. And here we are looking at strictly that partial pressure of water vapor. That is what drives the performance of the membrane, the primary factor, because there's also a secondary factor. The primary factor is the moisture, is the differential vapor pressure of moisture, of the water. That is very important to understand, because all of the other things that affect that partial pressure of water only affect the performance insofar that they affect the water vapor pressure differential. So the sample gas flow rate, the pressure is a big one. Adjusting the pressure of the sample gas makes a difference. The water content of the sample gas, of course, makes a difference. The purge gas flow rate makes a difference, because if you're flowing faster, you're going to remove more of the water, and it's going to lower the vapor pressure differential. Lower the vapor pressure and increase the differential, and therefore it's going to speed the transfer of water from one side to the other. The purge gas pressure also matters, and the purge gas water content. Now here you could see in our lovely diagram here, these blue jelly beans represent the water in the tubing coming out of the tube, and the jelly beans in red, yellow, and green represent the items that we want to keep in the gas stream for further analysis. So I just want to make a point of why this is important. We have a very large, in fact, there's a whole series of analyzer companies making a specific analyzer type. I will not name which ones they are, but what they do is, in order to increase their purge gas flow rate, what they're doing is they're taking a carrier gas from a combustion analyzer. The carrier gas is coming through, and they're recycling it back through as the purge gas. And in order to increase the flow rate, they said, well, we need twice the flow rate. That's what the PermaPure spec says. They're actually adding atmospheric air to increase that. Now, anyone should know, when you do that, you're also greatly adding to the moisture content of your purge gas, and you're actually slowing the transfer even when you're doubling the rate of the purge gas. So this is the kind of things that can be confusing to people, and people can go ahead and design an analyzer and design it with the wrong principles. So it's very important to keep in mind what the main factor is. There is a second factor, and this is also important. This is the membrane operating temperature, that the final dew point performance of the dryer is influenced by the dryer's operating temperature at the gas exit. With the lower the temperature, the better. This is an observed performance. We don't exactly know why this happens, but we know that it does happen. And so what I wanted to do is show here an example on the graph. You could see there's a dryer placed over the top. The sample comes in to the left wet and exits to the right dry. And along this this dryer there, the curves show the dew point of the gas along the dryer. So, and what you're looking at is this is actually an application that is coming off what I showed in one of those other graphs, a wet scrubber system, 70 degrees C dew point, 30% water. So if I'm taking the same sample and the entire dryer from beginning to end is at 100 degrees C, okay, I'm going to get a final dew point of roughly 35 degrees C. If I take the same sample, same flow rate, and I have the dryer finally operating at 40 degrees C, I'll get a dew point of roughly 0. And if I operate that dryer at the end with a 20 degrees C final operating temperature, I'll get a dew point of minus 25. So the operating temperature, and specifically the operating temperature at the exit of the dryer, is very important. These things greatly affect the performance of the dryer. And so what we want to do to facilitate this, number 5, this is our best practice number 5, we want to optimize the temperature profile of the gas pathway. So for every application, we want to be able to facilitate the flow rate going from a hot and saturated stream at the inlet and exiting cool and dry. And so I built this representation here of the dryer performance in 2 sections. Well, first I'm going to describe the lines on the curve. So the first line, the black line of the curve, that represents the temperature of the sample gas as it flows through the dryer. So you can see that it's reduced, especially in section A, and pretty much remains constant in section B. Then the red line is the dew point of the sample gas as it flows through the dryer. So at every part of way of the dryer, it's getting drier, and that dew point is being reduced as well. So that whole section A represents the portion of the dryer where the sample gas is taken from its initial dew point, let's say it's 70, let's say it's 100 degrees C, and I'm going to bring that down to the end of A where it's going to be 20 degrees C with a 20 degree dew point, which, lo and behold, is where our performance curve data starts with, right? In the B section represents the portion of the dryer performance that our performance curves, our published curves show. So what we like to say is that the additional length that you need to bring that sample down to meet our performance curves is roughly 50 to 100% of B. So roughly double the size of the dryer. If you have a longer dryer, you've got to double the size for what you would look at on the performance curve for the same flow rate. Now, also very important is that the dew point must always be lower than the gas temperature to prevent condensation. That is a very critical thing about the way these dryers work. You never want to have the sample gas condense out in the dryer, okay? Because when you do that, you lose the performance, and there's other issues as well. If you have pressure, you can burst the tubes, or the tubes can collapse, and you're just not going to get the right type of performance that you want. So to optimize the temperature profile of the gas pathway, here's a couple of best practices. Number one, heat the dryer at the inlet side for the first 12-inch to 1/2 of the length to prevent the sample gas from condensing in this portion of the dryer. The temperature should be 10 to 15 degrees above the dew point of the inlet gas. So in our systems, for example, we build a whole heater element to keep that first half of the dryer hot. And that's very important because we do not want to have any gas condense out in the line. The second part is make sure the outlet section of the dryer is cool. For example, a portion of the dryer might need to be rerouted away from hot areas in the analyzer, like next to the furnace, or cooled to a lower temperature. And additional water traps are unnecessary as the dryers can handle the volume. Now, a lot of analyzer companies that I know, they didn't understand when they first built these things of the incredible capacity of these Nafion tubing dryers to take out the moisture at high temperatures. So what they would do is they would actually, because they were afraid of the capacity issues, they would put a moisture trap and let water condense out naturally in the sample gas before it goes into the dryer. And that is really unnecessary. In fact, we don't recommend that precisely because you're going to condense out portions of the sample that you don't want to, that you might want to analyze. So I add a slide on troubleshooting. So when you're troubleshooting applications, factors to consider are: first, verify that the operating temperature is not contributing to poor performance if you're having poor performance. The inlet temperature is always above the dew point of the sample gas. Sometimes, not always, if you have a gas sample that is very hot, let's say 80 degrees C, and the dew point is 50 degrees C, sometimes you don't need to heat it. The heat in the sample gas is enough to make the dryer warm so that it never condenses. But those things we've tested in a lab. You can't really be sure what happens. When you're actually doing your experiments, you don't always know how much water is in the sample, and it's best to err on the side of conservatism, that you want these things to work correctly. You want to also make sure you have a temperature differential that is present along the length of the dryer, that the dryer is not running hotter than expected, and make sure the dryer is placed in an area where it runs cool, away from hot electronics, the internal furnace, and install an enclosure fan. There are many analyzers that have been developed where these dryers are hung on the backside of the furnace or next to a hot electronics card inside. And sometimes the entire enclosure itself, from all the electronics and fans and pumps and everything else that is in this equipment, sometimes the operating temperature inside is 35 or 40 degrees C, and that also contributes to lower performance. So let's go to best practice number 6, which is dryer sizing considerations. These are the considerations that you want to make to upsize your dryer. So number 1, oversizing the dryer can have huge upsides to perceived product performance. That means the product you're working on and the experiment you're working on, and extending your product operating life. There are no negative effects in contrast to sizing pumps or valves. So Perma was started as an offshoot of DuPont. DuPont, as you know, is a chemical manufacturing company, and the guys who were involved in this, this is what they knew how to do. They knew how to size valves and pumps, and they came out of that world. And you know, if anyone's done that before, you know that you have to properly size them. You can't go too high and too low. There's a fine point. With Nafion dryers, that's not really how it works. If you increase the amount of Nafion available to do the work that you need to get done in transferring the moisture, or drying your sample, it's going to improve your performance. The only negative effect is that the physical length can affect the analyzer response time and pressure drop. So in those cases, you can use one of our dryers that have multiple tubes in parallel. You will get much more surface area and actually shorten the gas path. So consider testing various lengths to determine the optimum size for your application. We have seen surprises along the way. And specifically, one of them was a batch style combustion analyzer where they used a continuous carrier gas. I think it was an argon carrier gas, and they would combust the sample, let's say, every 5 or 6 minutes. What would happen is that you'd have the sample was burned, and all the water was immediately dried and taken out into the dryer. And then in the time that it took for the whole system to regenerate, the sample gas continued through the dryer and actually dried out the dryer and made it ready for the next sample. In those cases, you might even be able to get away with a shorter dryer than you expected, because the Nafion is going to really suck up all that moisture really fast, even faster than in the continuous mode when you pre-dry it. So batch processing is a little bit interesting. We actually don't have any published performance data for that. We just have a lot of anecdotal evidence from the customers that we've had making batch style analyzers or doing batch style analysis. And there, again, if you come and tell us that's what you have, we can help you with selecting the right dryer for your application. So factors to consider when troubleshooting: review the customer target dryness levels, verify that the dryer is sized correctly for the application by reviewing the actual flow rate and water content of the sample gas, and determine whether there are other variables that could make a dryer with more surface area advantageous. This is important. Again, there's no downside to adding Nafion to a drying application other than cost. The applications will work better and last longer. So number 7 is considering dryer performance over time. So we get this question a lot. What happens over time, and how do we know we need to swap out the dryer? Well, the dryer performance may decline over time as the water pathways of the Nafion polymer membrane are affected by the sample or purge gas in the following ways. Oils or contaminants can physically block the water pathways. For example, complex hydrocarbons can coat the inner walls of the tubing. So any type of, and this also comes from any type of combustion analysis, any type of particle analysis. When you're dealing with any type of dirty sample streams or with heavy oils in them, what you do is you cover the pathways. The dryer actually doesn't stop working in itself. The water transfer mechanism is a fundamental part of the material. So you're never actually stopping that. What you are is blocking it by putting stuff in the way. Metals or cations are attracted to the surface and can chemically block pathways. So if you have any liquids that are formed on the surface, any type of metal ions are attracted to the sulfonic acid chains, to the negative sulfonic acid chains, and they also block water pathways, and they do that chemically. And ammonia salts can form on the surface from a reaction with Nafion and block water pathways. Dryer life is dependent on these factors, and in such applications, it should be considered a consumable. So let's look at extending dryer life with difficult sample streams. So 1, you can install particulate or coalescing filters before the inlet according to what may be present in the sample gas. We do that with our Perma Pure systems. For SEMS, for continuous emissions monitoring, we need to put filters before that because there's so much dirt and particulate that comes off the stack. You can add an ammonia scrubber to remove any ammonia in the sample before the inlet, and you can lower the operating temperature of the dryer. What you can also do is you can also specify a dryer with more surface area. If you know that the dryer performance is going to decline over time, usually you can extend that by adding more Nafion. Now, one of the things that I like to point out is when you replace the dryer depends on your application. So this is where it's critical to do the testing, to understand at what point are you going to need to replace the dryer when the dryer no longer performs the function that is necessary for your experiment or your analyzer. That's not really something that we can say. We don't really know. And I'll give you an example why. We installed or specified Perma dryers in a City of London particulate monitoring compliance project. They had 150 particle monitors mounted all over the place in the City of London to track PM 2.5 or the soot in the air. And the OEM on the project was wise. They actually, we co-developed a version of the dryer that had two connections in the dryer to put moisture sensors at the inlet and the outlet. And what they did is they measured, they continuously measured the performance of the dryer. They said, okay, here's the inlet coming in, what's the outlet coming out, how much is that sample being dried, and they'd monitor it in the computer. And when that performance was down to an unacceptable level, that's when they knew how to change the dryer. Well, the question is, how long did it take for these dryers to be replaced? Well, this is what was interesting about it. Some dryers lasted 6, 9, 10 years, and some in the very, very dirty areas only lasted 6 months. So and it's even questionable then whether you could have gone longer and it could have run longer. But I guess the point is that the applications can be very variable. There could be a huge difference between them. So some best practice number 8, conditions to watch out for. Condensing water at the inlet can slow moisture transfer and cause losses in analytes. Temperature must be less than 125 degrees C, as performance slows significantly above 90 degrees C. High temperature can melt the header. It's a picture there on the right. And there's also some pressure differential considerations. You see, we require that there's max 5 psi pressure differential when saturated with liquid water, as there is a bursting risk when wet if run at high differential pressures. Sample gas pressure must be higher than the purge gas pressure to ensure the tubing doesn't collapse. Especially when it's wet, it can collapse too. Now, this is a somewhat controversial statement because I think 95% of the Nafion dryers in existence have the sample pump ahead of the dryer, and as a result, there's a negative pressure in the tubing. So we realize this is actually the way most of these dryers are actually working. But the point is actually has to be made that with the sample being at a negative pressure inside, it also is the water transfer is also less. So you just want to be careful. A lot of people use it in that application. It's just not the best way to do it. But it might be the easiest way, the way most people use it, obviously. So the next portion, best practice number 9, is how do you generate the purge gas and vapor pressure differential for the Nafion tubing dryer, or how to integrate it into your analyzer design and experiment, and how to test it. So what we did is we put together all these curves and these diagrams to help you with setting up your experiment. And here is the first version, the best practice when dry purge gas is available. This is the way our performance data was made. You have your wet sample inlet coming in from the left, the dry sample going out to the right, and your purge air, instrument air comes in from the right and goes out to the left. And from there, here I have 2 little dots there with the DP over it. That's where you want to put your dew-point monitors or your moisture sensors. So typically your purge gas flow rate is 2 to 3 times of the sample flow to be adjusted as necessary for optimal performance. Here's where you want to put this on a test bench, and as you dial in your optimum flow rates, you can see the performance change. Our recommended purge gas is instrument quality compressed air. That has a dew point of minus 40 degrees C. It's clean and oil-free, very important. If you have oil in your purge gas, it's going to coat the outside of the tubing and slow your moisture transfer. And this is why it's got to be filtered clean. We call standard quality compressed air wet compressed air, which may carry oil and oil. Mist must be filtered clean as dirt and oil will collect on the dryer tubes. You can, however, use purge gas that is minus 10 or minus 20. You just won't get the ultimate performance that you expected. We have other customers that use a local air compressor. An air compressor with an ultra-low dew point rating may be deployed in an analyzer station for clean and dry purge gas. Many customers also use nitrogen or other cylinder gases like argon, other carrier gases, with a dew point of minus 60 or minus 70. And this can yield even better results than shown on our performance curves. But it is costly. And that's why you probably want to use instrument air. So the next one is a pretty good topic. It is how to use a vacuum pump to drive the water transfer. I discovered years ago that about 90% of Permapure's MD dryers were being used with vacuum pumps. And so I wanted to investigate why and how and what kind of performance that they did, because when I first joined 8 years ago, we didn't have any performance data with our dryers with vacuum pumps. It was all anecdotal. And we were making a statement, performance statement of what type of vacuum pump to use, and it really wasn't grounded in any scientific discovery. But here, since then, we've learned from our customers and from our own tests that there is a relationship between the dryer performance, the ultimate dryer performance, and your Permapure dryer. And you can see on the graph here, there's two performance curves overlaid. The one at the right is a typical vacuum pump performance curves, flow versus vacuum. As the vacuum is deepened or gets closer to full vacuum, your flow rate of the pump is lowered. And overlaid is the dryer performance of compared to the flow rate and compared with the vacuum pump. So you could see that as you reduce the flow rate and deepen the vacuum, you continue to get better performance out of your dryer. Your dew point is lowered and lowered and lowered until you reach this optimum point where you have the lowest possible dew point you can achieve with the system. Okay, where you have the lowest possible vacuum and at the same time enough flow to actually physically remove the water from the Nafion surface. This relationship is different for each combination of vacuum pump and dryer. And so when you're deciding to put in or use a vacuum pump with a dryer, you need to tune this performance. And don't take this lightly, because the difference between the performance of the dryer up here, of setting your vacuum pump up here and up here, could be the difference of doubling or quadrupling the length of the dryer. It's a huge impact. It's a huge cost impact. And so you can sometimes get away with a cheaper vacuum pump. That's also important. But you can also get away possibly with a shorter dryer if you're running the vacuum pump at a lower level. Okay, so this is an optimized system. That has to be done. This optimization has to be done for every combination of vacuum pump and dryer. So you restrict the flow of the purge gas by closing the needle valve while watching the moisture level at the DP sensor located at the sample gas outlet decline. And the sweet spot or optimal performance occurs when the vacuum is at its highest point and the flow rate, it is still high enough to sweep the water vapor away. Note, during testing, it might take 15 minutes or more for the dryer performance to stabilize in order to make a determination. It's also important, okay? That's because it's a chemical reaction that we're controlling. It just takes that amount of time to stabilize. So here is one version. This is where you're actually taking the air, atmospheric air, after it's been filtered, and you have your vacuum set up here. The vacuum has to be at the exit of the, after the exit of the purge gas, and your restriction has to be at before the inlet of the purge gas, because you want to pull that vacuum over the dryer. I mean, this is not funny, but there's a lot of people who put the restriction after the purge gas exit, and they were only pulling the vacuum here in this section after the purge gas, and they were wondering why they were telling me that the dryer wasn't working. So it's very important to put all this stuff together correctly. And I really want to say this out of respect for all of you. If any of you are doing any type of testing or development, or you have any experiment, and you find that the performance is not what you expected, please contact us and we'll help you connect this up correctly. Because in my experience, most people don't deal with these things on a day-to-day basis. And even when I was doing this stuff, it's very easy to make a simple mistake or overlook a detail, and then the product doesn't work. And so often people have come back to me and says, we could never get it to work, so we just stopped the project. Now that's a tragedy, not just for us that won't get any sales of dryers later on, but it's a tragedy for the customer who had a problem to solve and could not figure out how to do it. So I urge every one of you, if you're not getting the results that you're expecting out of this dryer system, please contact us and we will review the configuration of how everything is set up. I can't express that more. I've been around Perma many years, visited many customers, troubleshooted many applications, and I've seen this so many times that I need to make that clear in the presentation. So why would you want to choose this? Why would you want to choose a vacuum pump? Well, obviously you want to use it where no external purge gas is available or desirable. The vacuum level and flow rate, as I mentioned before, must be optimized. The air must be filtered clean. And the disadvantage here is that the drying performance is going to be dependent on the moisture level of the atmospheric air. It's going to change over time a little bit. And that is why a lot of people go to the second one here, which is recycling sample gas with vacuum. This is where the sample gas, after being dried, is rerouted back into the dryer as the purge gas under vacuum. This is actually a very effective way of doing it, especially if that gas is not corrosive. It provides a consistent dryness level at the output when run continuously. And you can improve the performance by further drying that sample gas in the second stage with the desiccant before it is routed to the purge inlet. This is actually the most common one, which is the split sample gas with vacuum. This is where you upsize the dryer a little bit, and at the exit of the dryer, you tee off the flow, where a portion of the flow is rerouted back into the dryer as the purge gas under vacuum. And the other portion goes into the analyzer or for the other portion for the other application. As I mentioned, this is the most popular method used by Perma. It's similar to the reflux method previously described. It choose the split sample method if it's not possible or practical to reroute the analyzer exhaust back into the gas dryer. The dryer must be upsized for the increased flow rate, adding a portion used for the purge gas to the sample gas flow rate required for the analyzer. Typically, I would say depending on your vacuum level, 30–40% needs to be brought back. If your vacuum level is going to be, I like to do 200 millibar absolute for a 5 times expansion. That's a very good vacuum level to achieve. And there you only need about 40 or so percent. If you don't have that kind of vacuum, you're going to have to increase that percentage and then also increase the total flow rate of the dryer. So like I mentioned, what's really good about this and the reflux mode, the recycled sample gas mode, is it provides a consistent dryness level at the output when run continuously. So let's troubleshoot the water vapor pressure differential. So as previously shown, the water vapor pressure differential is between the membrane sides is the primary performance factor. We must verify that the system is providing proper differential vapor pressure to facilitate moisture transfer. That means if it's not working, that means you don't have the vapor pressure differential. A lot of times people come back, that's what they say, it's not working. So the system has to be connected correctly according to the drying configuration used. The purge gas flowing concurrent to the sample gas. That means they're in opposite directions, not at the same direction. The purge gas is dry enough or vacuum level is sufficient to drive the required water vapor pressure differential. The vacuum pump is connected correctly with the restriction before the purge inlet. And the vacuum performance is optimized for the vacuum pump and dryer combination. Those are all points that you need to make when you're doing this work. So let's just go through some design-in challenges. These are things that I've seen at pretty big major customers. These are mistakes made by people, and for many of them, there's analyzers being produced today, very popular analyzers that have these problems going out the door. So number one, not understanding the true level of water in the sample gas. Running the hot and wet gas directly into an unheated dryer, causing condensation at the inlet and poor performance. Installation in the analyzer enclosure where it is so warm that the performance is ineffective next to the furnace or hot electronics, or no enclosure fan for ventilation. Not running the vacuum pump at its optimum performance level. There was a pretty big customer that was doing this. They put this monster vacuum pump in, and they were running it at a half a bar, and they were having issues in some applications with not being able to dry enough. And the solution was, just turn up the vacuum, and the problem went away. Like I mentioned before, mixing a dry purge gas with atmospheric air to increase the purge gas flow rate, reducing the effectiveness of the purge gas. Not installing a long enough dryer. Using moisture traps in the analyzer in places to trap excess water. Having the purge gas flow in the same direction as the sample gas. I know 2 analyzer companies doing that. By the way, it works. It just works about 30% less than it should. The performance is declined. And pulling a vacuum on the purge side with any purge gas flow. So when you come to us with an application, we usually get back to you with a list of questions to ask. We do this because the answers to the questions not only force our customers to get the required information, it also provides us the context for why the certain performance levels are needed. And in some cases, it can connect up to experience that we've had before with a similar analyzer or a similar design. So these questions are pretty important for everyone to answer. So we want to know a basic description of the application. Are you familiar with Nafion-based dryers and how they work? We find people that are not familiar with them really need a little bit extra time to understand how to get them to work. Because they're not necessarily so intuitive. They don't just work out of the box like an iPhone does or like a vacuum pump does. You just connect it up and hit the button. It's not exactly the same. We want to know what their application challenge is, what are they trying to achieve, what the chemical composition of the incoming sample gas is, and what the components are they're measuring. Are you removing or adding moisture to the gas stream? What are you using today? Incoming sample gas flow rate, pressure, and temperature. Incoming sample gas moisture content, the target dryness level required, that is, what level do you need? And what is the purge gas method that you're able to use? And any other notes that can help us understand what you're trying to achieve. Those are all important for us.